We start working with functions, which is a very important topic in pre-calculus. And we have kind of a long definition here, but it's very important that we get this long definition because we'll keep coming back to it over and over again. A function is a one-to-one correspondence. Now, I know that's a fancy word, but we're really just talking about matching. Okay? When we say a one-to-one correspondence, we're talking about an x being matched to a y. It's a one-to-one correspondence such that each element in set A, which of course is usually x. Okay? Each element in set A is matched to, this is very important, exactly one. Exactly one element in set B, which of course is going to be a y, usually. Which is usually a y. Okay? And then I like to put a semicolon here because there's a little other thing that we have to add. But 1b, which is usually a y, can be matched to more than one a. And when I say 1b, I'm meaning one y can be matched to more than one x. Okay, and I'm going to kind of show you what we're talking about with this and show you two different situations that kind of explains this. Okay? So let's look at two situations that will help us understand this. Situation one, leave a few lines or space, and then let's look at situation two. Okay, and this will help us understand this idea of a function. We have already talked about the quadratic y equals x squared. Okay? We've been solving those and so forth for a while. And if we were to look at the graph of this quadratic, we know that it looks something like this. It's a parabola. All right? And if I were to, let's say, come over to when x is 2, all right? If I put a 2 in here, what's 2 squared? 4. So this point on the graph is the point 2, 4. Okay? Now what I want you to notice is if I come over to negative 2, isn't the point negative 2, 4? Right? Now what I want you to notice is that we have, if we come back to our definition, I said here at the end, I said 1b can be matched to more than 1a. Well, that's exactly what we've got going on here. I have this single y value matched to two different, get a different color here, two different x values. Okay? That's okay. This right here is a function. All right? And that is totally okay for us to have that. Now let's look at situation 2. And situation 2, we're going to flip it around, and we're going to say y squared equals x. And the graph of y squared equals x looks like a sideways parabola, like that. Okay? And let's say we just come over maybe to an x coordinate of 3. Okay? Actually, I'm sorry, I want to come up to a y coordinate of 3. Sorry. We're probably going to have to come over a little bit farther on our x's. Let's come up to a y coordinate of 3 and a y coordinate of negative 3. Now, let's plug those values into my equation. Now notice, because of the way this thing is defined, y squared equals x, I have to put it in for y. So 3 squared is 9. So in other words, when x is 3, when y is 3, x is 9. All right, so if I come over here, if I want to match this one up, okay, and I've got to come over a ways, 4, 5, 6, 7, 8, 9. I need to extend my graph a little bit. To this point right here, I have the point 9, 3. And if I were to do the same thing, if I would have drawn my graph better, I would have the same thing down here. Because negative 3 squared is also 9. So this point right here is also on the graph, even though I've kind of got it messed up over here with my hash marks. I'll try to fix that real quick. Down here is negative 3. Okay? So look what this point is. This point is 9, negative 3. Well, guess what? This is a problem. This is not a function, because look at our definition again. We are supposed to have one element. Each element in set A is matched to exactly one element in set B. Well, we don't have that here. Okay? Look what we've got. This x, okay, this x of 9 is matched with two different y's. All right? It's matched with a 3 and a negative 3. This is not a function. Okay? And we're going to learn there's a real quick way to tell if it is a function or not, and we can do that using the, I'm going to get a different color here, the vertical line test. Look, wouldn't a vertical line hit this thing twice? Right? So if a vertical line hits the graph twice, then it's not a function. Okay? And we call that the vertical line test. And you'll be using that some tonight. Okay? We can say that this fails the vertical line test. Okay? Fails the vertical line test. Now, the next thing we need to talk about is this idea of inputs and outputs and being matched up. And the way that I always do that is by drawing what I call the function machine. And this is an outstanding way to think about a function. And so I just draw this kind of funny looking machine here. I just usually make a box, put some very simple legs on it, like that. And up at the top, I put a little hopper, like that, or a little funnel at the top. And then at the bottom, I kind of draw a little spout, like this. Okay? Funny looking machine, I know, but that's okay, it works. So here's what happens with a function. We have some kind of function. Let's say that the function is f of x equals 3x minus 4. By the way, that f of x is what we call function notation. And it is, in essence, the same thing as a y. Okay, I think you've seen that before. All right, f of x is the same thing as y, but we're not going to use y much more. We're going to use f of x a lot. So with a function, what happens is I put in an x, I put some x in, and then the function does something to it, and then it spits out a y. Okay? You put in an x into the function machine, and it spits out a y. In this case, let's try one. Let's say that I wanted to put a 2 in. If I wanted to put a 2 into the function machine, okay, so if I put in a 2 into this function machine, this function says that I'm going to do something to that 2, because that 2 is going to go right here for the x. So it's going to multiply that 2 by 3, and then it's going to subtract 4. So 6 minus 4 is 2. So in this case, it happens to spit out a 2. Okay, maybe that's a bad number to plug in because it looks like it spits out the same number, but that's not always the same case. Okay. What if I put in a 5? If I put a 5 into the function machine, well, then I need to do 3 times 5 minus 4. That's probably a better example. 15 minus 4 is 11. Okay? So you put in an x, and it spits out a y, and those correspond to points on a graph. Okay? These would both be ordered pairs. I could have an ordered pair of 2, 2, and I could have an ordered pair of 5, 11. Okay? And those would be points on the graph. So you put in an x, you get out a y. And it's very important to think about that in terms of the graphical relationship. This thing's just a linear of some kind. Okay? So you put in a 2, and you get out a 2. You put in a 5, and you get out an 11. Okay? We have to understand the graphical relationship between x's and y's when it comes to functions. Now, so again, we have to ask, what does the function do to the x? Well, in this case, it multiplies it by 3 and subtracts 4. All of these numbers that go in are called the domain of the function. That is very important that you learn that word. Domain is all of the x values that make the function work. We're going to give it a formal definition in a minute. All of the numbers that get spit out are called the range. Okay? So, we need to make some notes about this in an organized fashion. Let's go to a new page. And we'll just make these through several bullet points. Here's the first bullet point. F of x is the same thing as y. Okay, and I think we know that, but I just want to go ahead and label it. F of x is the same thing as y. Next, f is the name of the function. Okay. A lot of times we'll call it, function f, or function g, or function h, whatever. F is the name of the function. F of x is the value of the function. You put in an x, you get out some specific value. Okay? Domain. This is very important. Domain is all the x values that make the function work. All the x values that make the function work. All right? And then range is all the y values the function spits out. Okay? Domain is all of the x values, and I like to call those inputs. Okay? The domain, these are all the inputs. The range are all the outputs. Input and output. The x's get put in, the y's get spit out. Very important idea. I also like to think of domain and range as a pop machine. Okay? If I think of my pop machine, whatever your favorite kind of pop is, mine is Diet Mountain Dew. Let's say that, in a pop machine, don't you have a little place where you put in money? Right? And then at the bottom, it spits out whatever kind of drink you want. Okay? And I think you're all familiar with trying to put in our old friend, the our old friend, the dollar bill. You got George here in the middle. Okay? And you try to put that dollar bill in, and it's kind of wrinkled, and so you kind of flatten it out, right? And you put it in, and ring, and it spits it back out. So you kind of smooth it out a little bit more, and then you try to put it back in, and you're kind of getting mad because you're thirsty and you want to drink. Well, if you think of that in terms of x values, not every function if you think of the dollar bill as an x value, okay, not every x value will go into a function. And we're going to talk about some of those in upcoming days. Some functions will spit out an x value because it won't work. And so we're going to talk about that a lot in the future. I want to look at some examples like you're going to see in homework. These are pretty easy. They're going to ask you, is the relationship a function? And there's several ways that we could look at these. We could look at it graphically, like I already talked about. They could give you a graph of some kind, or maybe they ask you to graph it. How about, haven't we already talked about circles? Right? Remember we talked about circles, and wherever the center of the circle is, it doesn't matter. Remember when we did circles? X minus whatever squared, x minus 2 squared plus y minus 3 squared equals 4 squared. Remember when we did that? Well, let me ask you a question. Is that circle a function? Does it pass the vertical line test? No. Okay, this is not a function. Okay, because it fails the vertical line test. We have one x matched to two different y's. That is a problem. All right. Then sometimes they'll give you tables. Okay. They'll give you a table and they'll say, okay, here's your domain and here's your range. Okay, remember domain, are those x's or y's? Domains are x's, range is y's. And they're going to give you this list of numbers like 18, 19, 20, 21, 22, like this. And then they're going to give you a list of numbers for the range, 40, 50, 60, 70, 80. And then they're going to draw some arrows, matching them up. Okay? Let's say that the arrows look this way. Matched there, matched there, matched there, like that. So they've got those arrows matching up numbers like I've got drawn there. Now, so the question is this a function? For it to be a function, every x can only be matched to one y. Do we have a situation where that's not true? Look at 19. 19 is matched to two different y's. So no, this is not a function. Now let me ask you a question. Is this okay? Is that okay? That's okay. It's okay to have two different x's matched to one y, but we cannot have this. All right? They may give it to you in a set of points like this. They may say, okay, set A has the points 2, 4, 6, and 8, and set B has the points -10, -8, -6, -4, something like that. And then they say, okay, here is the function. The function is this set of points. 2, -10, 4, -4, 6, -8, and 8, -6. Okay, they're going to give you a set of points like that. And they're going to say, okay, this is your function. Or they're going to ask you, is this set of points a function? So we have to ask, is every x matched up to exactly one y? And I think the answer in this case is yes. Every x, 2 is matched to -10, 4 is matched to -4, 6 is matched to -8, and 8 is matched to -6. If we would have had one other point that looked something like this, right? If I would have had one more point listed that said 2 is also matched to -8, then it would have been no. Okay? But that wasn't the case. All right? So the answer in this case was yes. All right? So they're also going to give you they're going to ask, how about y equals the square root of x minus 5? And they're going to say, is that a function? Well, you know what you're going to have to do? You're going to have to graph it on the graphing calculator. All right, you have to graph the square root function. I'm going to tell you what that one looks like. It looks like this. This is the square root function. Okay, you're going to learn all these functions and know them very well. But if that is the square root function, or if that's the equation I'm given, is it a function? It is, because it passes the vertical line test. It only hits it once. Okay? Yes, it is a function. Okay? What if they gave you this one? -x plus y squared equals 1. And they said, is that a function? Well, we kind of talked about one like that said y squared equals x. So I think you know what the answer is. But what if you wanted to look at it on your graphing calculator? You'd have to solve it for y. Okay? And I'll go ahead and tell you what that is. You add x to both sides and then take the square root. It's going to be y equals plus or minus the square root of 1 plus x. How would I enter that on a graphing calculator if I wanted to? You'd have to enter it as two equations. You'd have to enter y1 as the square root of 1 plus x, and you'd have to enter y2 as the negative square root of 1 plus x. That's how you would have to graph it on your graphing calculator. You'd have to graph both of them at the same time, and then when you did that, you would see that this thing looks like some type of sideways parabola. Okay? So if you needed to graph that on the graphing calculator, you would have to graph y1 and y2. Okay? And then you could get a picture of it on your graphing calculator. We're going to stop there for today.